Happy New Year, everybody. That's a great way to start off a recording. Happy New Year. Welcome back. Anyone still sticking to their New Year's resolutions? I bet at the top of everyone's New Year's resolution was do more math, right?
Yep.
Do more math. It's good for you, and it's good, right? It tastes good, and it's good for you, math. So hopefully, if you haven't made that resolution, you can make it now. You could say 17th is like your new New Year's Eve, and then the 18th will be your new New Year's. And you could start. Every day is a brand new day. Every day is an opportunity to begin brand new, afresh, with new goals and new ambitions, right? So stick doing more math in there. It's good for you, and it tastes good. You got to admit it tastes good. So what are we going to be eating this morning? Well, it's the last section in chapter 4, 4.5. We're putting all of our exponential prowess and all of our log skills together in one section, and the whole purpose is to solve equations. Okay? Whole purpose is to solve equations. Your test again will be next week. Could be Monday, could be a Tuesday. You don't know. I'll let you know. It takes a little time to get through this section, but as soon as we're done, we'll know. Okay? So an exponential equation. An exponential equation. We're going to start with exponential. It's going to be called a conditional equation. I'll get this one, Mackenzie. I'm over here. Rhino, come on in. It's a conditional equation. All right, so let's review what a conditional equation is. A conditional equation is an equation that's only true under certain conditions. It's not an identity, so it's not always true. It's not a contradiction, so it's not never true. And it's not a name equation like f of x equals something. It's only true for a certain value of x or certain values of x. What do we do with conditional equations? We solve conditional equations. It's an activity. It's better than Sudoku. I don't know if it's better than crossword puzzles, though. Those are my jam. Everyone thinks that I like Sudoku because it has numbers and I'm a math teacher. So, like, in the past when I've been in the hospital, I've had a lot of people come and they bring me, like, Sudoku books. And I'm like, oh, man, you made me feel worse. Sudoku gives me a headache. But their goal was to try to make me feel better. So I put on a fake smile and I was like, thanks, Sudoku, right? Yeah. If you want to make me happy, bring me crossword puzzles. Or bring me some math equations to solve.
Would you actually be happy when we just solve
Actually, I would. I actually would. But again, I'm not most people, Brady. Okay, so if we have an equation like this, 3 to the x power equals 11. That's a conditional equation. We're going to solve this one, okay? Now, we could probably try to do it intuitively and see how close we can get to finding what x is. Could x be 1? Is x equal to 1?
No.
No, because 3 to the first is what? 3. That's too small, right? So we need something bigger than 1. How about 2? Could x equal 2? No, because 3 squared is what? 9. That's still too small. Could x equal 3? What's 3 cubed? 27. Oh, crap. Now that's bigger than 11. So the best I could do intuitively here is to say that x is approximately 2 point something, right? Or additionally, you could say x is between 2 and 3. You can pinpoint it, or you can narrow it down. You could trap it, I should say, maybe. You could trap it between two numbers on the number line. But that's about as good as it gets, right? Now, because the answer is not an integer, we need some way to figure out what x is, all right? So notice right now x is trapped inside of the exponent. X is trapped inside of the exponent. So let's think of what we could do. Well, how do I unexponentiate something base 3? We've already talked about it. We log base 3 it. So there's two different routes we can go. I'll show you. Let's go down the first route over here. We're going to take the log base 3 of both sides. We're trying to peel back the layers here. So it's going to be log base 3 of 3 to the x equals log base 3 of 11. When we take the log of both sides, we don't just squeeze it in on the first line like we do when we exponentiate both sides. We take a whole other line and we write the log in front. Okay? Now, if logging base 3 and exponentiating base 3 are truly inverses of each other, what should become of the left side? That is, what is log base 3 of 3 to the x? We get x equals, hey, that's our goal, right? Is to declare x equals something. And I have it. It's log base 3 of 11. Okay? Now, when we have log base 3 of 11, that's probably the most concise answer we can have. But what I'm going to do is, in this class, I'm going to try to put most of my answers, if not all of my answers, in terms of log base e. What's another name for log base e? Natural log of x. So let's take the change of base formula and apply it to log base 3 of 11. That's going to be the natural log of 11 over the natural log of 3. Now, that's not a very fulfilling answer to us. We were hoping for 2 point something, right? But guess what? This is a simplified exact answer. And we can carry this around in its purest form for any subsequent calculation and not have to worry about rounding error. Now, if you are interested in, of course, what that comes out to be, we can go to the Minnesota standalone calculator and we can actually type it in. And this is just to kind of fulfill our curiosity. This would not be an answer on a test. I wouldn't put decimal answers on a test here because I want you to be the calculator. I want you to do the work, and I want the answer to be exact. So let's just see what it is. Do you think it's going to be closer to 2 or closer to 3? It should be closer to 2, right? Why is that? It's on the smaller side. 11 is closer to 9 than it is to 27, right? So let's just type that in. We'll hit alpha x equals, and we get the natural log of 11, close parentheses, over the natural log of 3, close parentheses, and we'll put squiggles here, 2.182 or 2.183. If you round or truncate to 3 decimals, which is the standard obligation in this class, when it doesn't terminate prior to 3, we report 3 decimals. Okay, that's pretty cool. Now, we could check our answer on the calculator. Watch. The calculator has all of those decimals stored in its memory. Look what we could do. We could check. We could say 3 caret raised to the power of, and then I can hit second negative, which recalls the answer from the previous line. See that? If this works, it should give me what? 11, okay? It gives me 11. Now, notice if I typed in just my answer, 3 caret to the 2.182, is that going to give me 11? It gives me 10.999999999 which is why we don't want to use 2.182 or 2.183 for a subsequent calculation. Does that make sense? If it's our final answer, great, report 3 decimals. But if we want to use this for something else, this was just a calculation that we needed on for something else, we want to use it in its purest form, undiluted form, and that's the natural log of 11 over the natural log of 3. Okay? So, there you go. That's the first way to do it. Now, because everything's going to end up in terms of the natural log anyway, let me show you the way that I would encourage you to do it. There's nothing wrong with taking log base 3 of both sides, but I would recommend this. Let's take the ln of both sides. Let's take the ln of both sides. So this is going to be the natural log of 3 to the x equals the natural log of 11. It's going to end up in natural log form anyway, right? Now, what becomes of the left-hand side? Is the natural log of 3 to the x just x anymore? No, because I have base e and base 3, and those don't undo each other. But I can use one of the properties of logs that says an exponent on the argument can go where? Out front. So that becomes x times the natural log of 3. And now the natural log of 3 is just a number. It's just a number. So what would I do if I wanted to solve for x and it's times the number? I would divide both sides. Oops, I saw some strange looks. I put 3 on that side. It's supposed to be 11. I would divide both sides by the natural log of 3, and it would divide out on the left, and I'm left with the natural log of 11 over the natural log of 3. Is that the same thing we got over here? It is. Which is easier? I don't know. They're both viable methods. Now, even if we did the natural log, you could condense this down using the change of base formula, and you can condense it down to log base 3 of 11 if you needed to. The change of base formula is very useful. Okay, so I'm not going to take the log base whatever anymore in any of these examples. I'm just going to use the natural log every time. E is the natural base, right? Like math, it tastes good and it's good for you. It's all natural. All natural. Okay. Oops, I lost my text. Let's see. Sometimes that happens. You got to get out and get back in there. Oh, yeah, look, I was writing over my words. There we go. Okay, any questions on that? Okay, now, having looked at the first exponential equation, where the answer wasn't an integer or a rational number, we're going to look at the first method that you should consider when you have an exponential equation. I call it the GTBTS method, and I've already introduced it to you, okay? It's called getting the bases the same, the GTBTS method. Here's what it says. We've already seen this theorem in the previous section. If b to the x equals b to the y, because exponentials are in fact one-to-one, then if the bases are the same, we can equate their exponents. Okay? Now, if you do that, you get it by a theorem. So you're going to have some transitional word like so or therefore. If you don't want to use this theorem, you could actually do what to unexponentiate b both sides? What could you do? What can I do to both sides to unexponentiate base b? I can log base b both sides. So if you don't want to use the theorem, you're going to have to show this step here. What's log base b of b to the x? X. What's log base b of b to the y? Y. You get the same result. Okay? But if you use the theorem, you can save this step. You don't have to write this step. Save if you use this theorem. THM. Let's try it out. Solve each of the following by the GTBTS method. So, first of all, this is a conditional exponential equation. How do we know it's an exponential equation? There's what on both sides? There are exponents on both sides, but what's special about the exponents? The variable is in the exponent. There you go. When you have a variable in the exponent, you have yourself an exponential equation. Now, you could just jump in without even looking. You could take the natural log of both sides. That's like just cannonball. You're jumping into this body of water, and you haven't even looked to see if it's deep enough or if there's a stick right there where you're going to land or an alligator with its mouth open waiting for you, or there's 20 feet deep of water and you can splash without a problem. Okay? You got to size up the problem. Look before you leap is what they used to say. Look before you leap. I have a base of 9 on the left and a base of 27 on the right. First of all, can I write 27 as a power of 9? No. 9 to the first is 9. 9 squared is 81. But can I write both 9 and 27 as a power of a third-party base? Yeah, they're both powers of what? 3. So I think I can get the bases the same. If you can get the bases the same, it's going to be a little bit easier than taking the natural log route. So here's what I'm going to do without a stupid freaking highlighter. I'm just going to say it's 9 to the 2x equals 27. Oops, I'm going to leave the 27 out to the x minus 1. So I'm just putting parentheses where the 9 and the 27 used to be. And now for 9, I'm putting 3 squared. And for 27, I'm putting 3 cubed. That's my first step. Inch by inch, it's a cinch, right? Our goal is to communicate our results, not just get results. The process is part of the product. Okay, now I can use my rules of exponents that says when you raise a power to a power, what do? You multiply. So I'm going to get 3 to the 4x, and if I distribute over here, I get 3 to the 3x minus 3. Now, did I get the bases the same? 3 to the something equals 3 to the something, yes? All right, so I can either take a whole nother line and write log base 3 of both sides, or I could just say, so 4x equals 3x minus 3. Or you could put the therefore symbol. If you want to use the little triad right there, whatever you call it, you could use that instead. That's kind of a cool symbol. But that means that it's a consequence of something. It's a consequence of the theorem. So 4x equals 3x minus 3. And now we're back in algebra 1, aren't we? We subtract 3x from both sides, and we get x equals negative 3, and there's your answer. Very, very easy once you get the bases the same. You equate the exponents, and you've made the problem much easier. In this case, we took it from exponential to linear. All right, comments or questions on that one? But easy, right? Nothing to it. All right, let's look at letter B. I got 100 times 1/5 to the x divided by 4th power equals 4. Why is it an exponential equation? Well, they both have exponents, really? Oh, 4. Oh, yeah. Okay, cool. 4 to the power of 1. So they both have exponents, yeah. But what's special about one of the exponents? It's a variable. There you go. That's what makes this an exponential equation. I have a variable in the exponent. Can I get the bases the same?
Yeah.
I have a 1/5, which I can write as the power of 5. And on the right-hand side, I have a 4. Can I write 4 as the power of 5 very easily? No. Oh, and by the way, I also have this dude that's called 100 sitting in front of my base. You know what? Our first step here is to isolate the base with the variable. I want to isolate the base with the variable. So how do I get rid of the 100 if it's out in front being multiplied by that? I divide both sides by that. So if I haven't really done anything new, I'm just doing algebra 1. I divide both sides by 100. So it divides out on the left, and on the right I get 4 100ths. Well, doesn't 4 100ths simplify? It simplifies down to what? 1/25. Hot diggity donut! Now I have a 1/5 base on the left, and really on the right, since it's to the first power, I have a 1/25. Those are both powers of what? 5. Now you could write both sides as a power of 1/5 if you like, but most people don't like fractions, do they? So let's write them both as powers of 5. So I'm going to have blob to the x divided by 4th power equals blob to the first power. All right, 1/5 is the same as 5 to the negative first power. And 1/25 is the same as 5 to the what power? Negative second power. Very good. And now I'll multiply, so I get 5 to the negative x divided by 4th power equals 5 to the negative 2th power. Did I get the bases the same? I did. So I'm going to put so. I like so instead of the therefore triad because it's short, it's 2 letters, and it just has this blue collar feel to it, right? Like we're working men here. We're not elite snobs. This is so, right? So negative x divided by 4 must equal negative 2. Oh, and now how do we solve for x? Multiply both sides by, not 4, but negative 4, because that'll divide out over the left side, and we'll get a positive x, and then negative 4 times negative 2, x equals 8. And there's the answer. Do I need to box it at the bottom?
Yeah.
Do I need to box it at the bottom? I don't need to box it at the bottom. Remember, when you work straight down, and we're keeping the equal sign all the way down, the bottom line is considered your answer. Now, sometimes you feel such a sense of accomplishment that you want to put it in a box to highlight it. Like, look, I did it. I got the answer. That's what you wanted. I got it. So there's no harm in putting it in a box, but you don't need to if it's the bottom line. We're working straight down. Remember, if we run out of room working vertically, we draw a vertical line and we work in a new column. We don't just keep working left to right, okay? You shouldn't have 2 equal signs left to right. All right, so far so good. So sometimes we got to do a little bit of work before we get the bases the same, and that's to isolate the variable pieces. Okay, let's look at part C. Who in Devil's Nation created this monster? What in tarnation is that? Well, inch by inch, it's a cinch. Let's look at the variables first. They're attached to bases, right? One of the bases is the cube root of 16. The other base is the 5th root of 8 divided by 2. What is the common multiple that those 2 bases can be written as powers of? 2, right? 2. That is part of your thinking. That's you sizing up the problem. You have to come to that realization. I can write those as powers of 2. I'm gonna rejoice that powers of 2, everybody. So on the next line, guess what my goal is? I'm going to go through and I'm going to try everything as powers of 2. Now, the 1/4, as it turns out, can also be written as a power of what? 2. Okay, so look, I'm going to have 1/4, the cube root of 16 to the x plus 4th, and then I'm going to have equals all of this to the 2x minus 1 power. All right, go gadget 2. Here we go. 1/4 is the same as 2 to what power? -2. Some of these are going to be easier than others. We might have to take another line if we need to do it in baby steps. The cube root of 16, can we do that in a single step? 2 to the 4/3. Very good. 2 to the 4th is 16. We get rid of the cube root by putting the 1/3 as the base or as the factor. So we get 4 times the third, which is 4/3. Good. All right, now over here we might have to do it in 2 steps because there's a numerator and a denominator. The 5th root of 8 is the same as 2 to what power? 3, because that's 8. 2 cubed is 8. And then to get rid of the 5th root, I put it over 5. And the bottom, of course, is already 2 to the 1st. So I'll just put a 1 there. I wrote everything as powers of 2. Now your dear Aunt Sally is dictating what you do next. Please excuse, okay? If I look at the left-hand side, inside the parentheses, is there anything I can do inside the parentheses? No. So now I look for the E in PEMDAS, which is exponents. I do have an exponent right here, don't I? So I'm going to bring down the 2 to the -2nd because there's nothing to do there. And now the E, I'm going to multiply those. So I get 2 to the 4/3 x when I distribute plus 16/3. I'm just distributing the 4/3, as ugly as you may think it is, to the x and to the 4. And I get 4/3 x plus 16/3. So far, so good? I know you're having fun. Now, on the other side, I got to do PEMDAS again, but this time inside the parentheses, is there something I can do? I can divide those because the bases are the same. So that's going to turn into 2, stupid highlighter, 2 to the 3/5 minus 1. What is 3/5 minus 5/5? -2/5. Good. Because 1 is the same as 5/5. So 3 minus 5 is -2. And that's still to the 2x minus 1th power. So that's all I'm doing on this line. A little bit on the left, PEMDAS. A little bit on the right, PEMDAS. Right? PEMDAS. That's all we're doing. All right. Now back on the left-hand side for the next line. The P is gone. There's nothing to do inside the parentheses. The E is gone. Now we're multiplying. I got 2 to the something times 2 to the something. What do I do when the bases are the same and I'm multiplying? I add the exponents. Very good. Now, the exponents are different types of terms. I have an x term and I have a constant. I can only add like terms. So the 4/3 x, there's no other x term. It's still going to be 4/3. Off to the side here, I have to do -2 plus 16/3. I got to add those constants together. Well, -2 is how many thirds? It's -6/3. So I get really -6/3 plus 16/3, which is what? 10/3. Remember when we worked with fractions a lot earlier in the year? And I said, don't be afraid of fractions. You're going to have a lot of fractions in these problems. You know why? Because I'm the devil that created them. I love fractions. I love you working with fractions. It makes you a better person. That's it for the left-hand side, isn't it? The left-hand side is now consolidated down to a single power of 2. Now our goal is to do the same thing on the right-hand side. PEMDAS. Well, now we're exponentiating. There's nothing to do inside the parentheses. We're exponentiating. What is the rule when we're exponentiating? What do we do with the exponents? We multiply. So I'm going to have to distribute now. So I get -2/5 times 2. That's -4/5 x. And then plus 2/5. I have succeeded in getting the bases the same. I have 2 to the something equals 2 to the something. So instead of logging base 2 both sides, I can skip that step of logging base 2 both sides. I can just equate the exponents. So 4/3 x plus 10/3 must equal -4/5 x plus 2/5. Bless you. You're so welcome. All right, now I'm at a fork in the road here. I can either A, keep working with the fractions like we've been doing, or B, I can multiply both sides by the LCM of all your denominators. What is the LCM of 3 and 5? 15. If I wanted to multiply both sides by 15, I could get rid of the fractions, and then the fraction will reappear in the very last step when I solve for x. What do y'all want to do? What would you be more likely to do yourself? Keep going with the fractions or eradicate them? Kill them? That was pretty blunt, Wyatt. Eradicate kind of doesn't sound so bad, but kill them just sounds like murder. All right, here we go. I'm putting parentheses around. I would work with the fractions personally, but I'm a fraction guy. We get along. Now, when I distribute, I'm not going to multiply and then divide. No, no, no. I'm not going to go big just so I can turn around and go small. We go small first and then we go big, right? We divide and then we multiply. So what's 15 divided by 3 in the first term? 5. What's 5 times 4? So we get 20x. Very good. Plus, what's 15 divided by 3 in the second term? 5. 5 times 10 is 50. Okay. Now we do the same thing over here. 15 divided by 5 is 3. 3 times negative 4, negative 12x. And then 15 divided by 5 is 3. 3 times 2 is 6. It's not bad. It looks a whole lot more friendly, user-friendly, when you kill the fractions. So now let's just collect x terms on the left. So the 12 comes over, combines with the 20 to give us 32x. The 50 comes across over here and gets subtracted from the 6. So we get negative 44. Something like that. Check my math, right? Negative 50 plus 6 is negative 44. Yeah. And then 20 plus 12 is 32. Yeah. So here's where the fraction reappears on the last step. We divide through by 32 and we get negative 44 30-seconds. But hey, that simplifies, doesn't it? There's a common factor of what in each of them? There's a 2 and there's a 4. The 4 is the GCF. So that's going to be negative 11/8. And notice I worked straight down the entire time. I almost needed a new column there. If I needed a new column, it would just be for x equals a negative 11/8. In fact, I'm just going to go ahead and do that. I don't want to go to the next page. It makes my notes a little bit nicer. And that's fine. You got a new column with one thing on it. Now, nobody, I don't think, unless you're a wizard or some kind of demon, can look at the original equation and say, yeah, negative 11/8 works. Negative 11/8. Negative 11/8 works. Yeah, definitely. Right? But through a algorithmic process, step by step, using PEMDAS, right? And to get the bases the same, we were able to hone in on it, right? And we found it. We revealed the condition under which the equation is true. And it's a nice little rational number, right? Which is better than an irrational number or a log number. It's still a relatively nice number. It's not an integer, but it's still a rational number. It's a ratio of two integers. All right. That one was fun. You got to admit, that was fun. That was like a Friday New York Times puzzle, crossword puzzle. This is like a Monday. If you've ever worked at New York Times crossword puzzles, they get harder throughout the week. So Monday is pretty easy. You get to Wednesday, and you're sweating a little bit more. It's referring to like these books or these plays that no one's ever read or seen. But then you get to Friday, and Friday is just like, holy moly, I didn't know this was a word, or I didn't know this person existed, or this was a peace treaty in 1923. I didn't know that. It gets really, really hard. Okay. We just went from a Monday to a Wednesday to a Friday New York Times crossword puzzle. And we did it together. Inch by inch, it's a cinch. Mile by mile, it's a trial. Oof. Yes, I would insist that you do. It's important to stay properly hydrated. All right, any questions on the GTBTS method? Does the GTBTS method always work? Does the GTBTS method always work? No, remember the opening example here? Can we write 11 as a power of 3? We can't write 11 as a power of 3. So there has to be another way, and that's where the logs come in, right?
You could write 11.
Do you know what it is?
Yeah. ln over.
Okay, smarty pants. Right. Yeah. Okay.
Now I do.
Right, now you can. Okay. All right. Solve the following equations. Give simplified exact answers. 3 decimals. Okay. So now we're getting to the part where I don't think the GTBTS method is going to work. And our phones are going to not be any help to us either. Yeah. 9 times e to the dos equis, that's an alcoholic beverage, equals 30. Right? The most interesting man in the world. They got rid of that ad campaign. That was a good one. I wish they'd bring that back. He doesn't always do math doesn't always solve math equations, but when he does, they're exponential. All right. So we know we have an exponential equation because we have a variable x in the exponent. I need to get at the 2x. So as you walk up to the left-hand side, what's the first thing that's in your way of getting at the 2x? No, even before the e. What's blocking the e? The 9. The 9 is in your way. I need to get rid of that 9 so I can isolate the exponential factor. The exponential term is isolated, but now I need to get at the factor. So how do I undo multiplying by 9? I divide both sides by 9. So I get e to the dos equis equals 30 divided by 9. That's your first step. Now, simplify along the way. Simplify early and simplify often. 39ths. Does that simplify? 10 thirds? Yeah, it simplifies to 10 thirds. So simplify early, simplify often, simplify along the way. Now, here's your question. I've isolated the exponential factor on the left-hand side. Can I write 10 thirds as a power of e?
Yeah.
What is it? You don't know? I thought you said you would know for next time. Off to the side. Yeah, 10 thirds is actually e to the natural log of 10 thirds. Would y'all agree? Because what's e to the natural log of blob? The blob. So if you want, I would not recommend doing it this way, but if you want, you could write 10 thirds as e to the natural log of 10 thirds, and then you got the bases the same, and then you can say 2x equals the natural log of 10 thirds. That's one way to do it. I'm just going to say, no, I can write 10 thirds as a power of e. So what comes to the rescue? ln to the rescue, the natural log to the rescue. We're going to take the natural log of both sides. Take the natural log of both sides. Now, look on the left-hand side. This is more intuitive. What is the natural log of e to the dos equis? Dos equis. I don't know if you're allowed to say dos equis if you're not over 21.
No, you can say it.
Oh, you can say it. You just can't drink it. Oh, okay. So you're good, Brady. Dos equis. And then over here on the right-hand side, we get the natural log of 10 thirds. Now, that's the same answer you would have gotten if you had written 10 thirds as e to the natural log of 10 thirds. And it would be just as many lines. Okay? Writing 10 thirds as e to the natural log of 10 thirds requires a little more insight. You're building something up. You're creating something that's not there. Whereas taking the natural log of both sides is just something that works every time. So I think it's a little bit easier to take the natural log of both sides. Now I'm almost there. How do I solve for x if I'm multiplying it by 2? How do I undo multiplying by 2? Divide by 2. So if I divide by both sides by 2, I get the natural log of 10 thirds all over 2. Did I solve for x?
Yeah.
I sure did. Now, let's say that this is a multiple choice question on your test next week and there is no calculator. Do you think that would be an answer choice as it's written? No. No. Because it looks like a complex fraction. You've got a 10 thirds in the top as the numerator of a fraction where there's a 2 in the denominator. I don't like complex fractions. So here's what we're going to do at the end of our answers. We're going to play with the logs on the back end of our answer. Okay. Now there's 2 ways to write this. The first one is to say dividing by 2 is the same as multiplying by a half. That's one way to do it. To me, that already looks better. Does it look better to you already? I like that look better. So that could be an answer choice. But what else could we do in the numerator since I have the log of a quotient? Oh, yeah, okay. So let's go back to the left-hand side. I could even move the 1/2 back up as an exponent. Speaking of playing with the logs, that would be 10/3 to the 1/2 power. And of course, anything to the 1/2 power is the same as doing the what with it? Square root of it. So there you go. I like that, Andrew. I like that. I wasn't even going to go that far on the left-hand side. But that could be an answer choice. The natural log of 10/3 divided by 2 is the same as the natural log of the square root of 10/3. Now, what if I keep it dividing by 2? What else could I do with the natural log of a quotient? I could turn it into the natural log of 10 minus the natural log of 3. The natural log of 10 minus the natural log of 3. That's another way to kind of ease the tension of the complex fraction. Now I don't have a fraction in the numerator anymore, do I? Okay, so I can leave it like that, or I can write it as 1/2 times the natural log of 10 minus the natural log of 3, or I can distribute the 1/2 and say it's 1/2 natural log of 10 minus 1/2 natural log of 3, and then I could bring the 1/2s back up on both of them and say it's the natural log of the square root of 10 minus the natural log of the square root of 3. These are all equivalent answers. Every single one of these lines that are highlighted are the exact same answer. If you type any of them into your calculator correctly, I should say correctly, you're going to get the same decimal answer. I'm not interested in what that decimal answer is. So this is why the test that you test on this section is so much darn fun, because you don't stop with your answer. You play with logs at the end of your answer, and you have to match it up to a correct answer choice. Okay. Now, if I really wanted to keep going, what could I actually do with the natural log of 10? If I really wanted to keep going, I could say the natural log of 10 is the natural log of 5 times 2, which is the natural log of 5 plus the natural log of 2. I could break it down into its prime factors even more. And if I stick this right here, right there, now I'll have 3 terms in the parentheses instead of just 2. Could I do that? Would I do that? Maybe. Depends how bored I get this weekend when I'm making your test. Okay? I like to play with logs. College Board, if you go on to take the AP Calculus exam, College Board also loves to play with logs. So you need to be comfortable with manipulating your answer on the back end to match it to an answer choice. Okay? All right, so who came to the rescue there when we couldn't GTBTS? Natural log, ln. ln. I didn't bother taking log base 10/3 or log base e. I just said log base e all the way. All right. Let's look at example B. It's an exponential equation. I have a variable on both sides in the exponent. I want to solve for x. First thing you consider is the GTBTS method. Can I get the bases the same? Easily. Can I write 7 as a power of 2 or 2 as a power of 7? No, I can't. Okay? Not unless I use that little trick that I just did, that 7 is e to the natural log of 7 and 2 is e to the natural log of 2. Okay? I'm just going to say, I'm going to take the ln of both sides. Now, the first thing that you want to also do after you settle on taking the ln of both sides is you want to isolate the exponential factor. So there's really nothing in front of these other than a 1. Like over here, there was a 9. I divided through by the 9. I'm just going to go ahead and take the natural log of both sides. So here we go. I'll just say ln to the rescue. So I get the natural log of 7 to the x minus 5 equals the natural log of 2 to the 3x plus 4. Now, having the log in front allows us to do what with the arguments, or the exponents on the arguments? Where do those go? In front. I'm just going to pretend I meant to do that with the highlighter. Now, because I'm bringing binomials, 2-term dudes out front, I need to make sure they're in parentheses. Otherwise, it's not going to be the entire thing. It's just going to be the 5 with the natural log of 7. And over here, the same thing, 3x plus 4 in parentheses times the natural log of 2. All right, now, at this point, I want you all to just understand that the natural log of 7 and the natural log of 2 are just numbers. That's all they are. They're numbers. What would you do if those had been just a 7 and a 2 instead of a natural log of 7 and a natural log of 2? What would your next step be? Distribute. There you go. You have to distribute the numbers so that you can collect like terms on both sides. You have to distribute your numbers so that you can collect like terms. So I'm going to distribute the natural log of 7, and I'm going to distribute the natural log of 2. So I'm going to get x natural log of 7. Instead of the natural log of 7x, I write it as x natural log of 7 minus 5 natural log of 7 equals 3x natural log of 2 plus 4 natural log of 2. Now I have x terms and numbers. I have x terms and numbers. I'm going to collect my x terms on the left-hand side. So I'm going to keep the x ln of 7 on the left, and I'm going to red rover, let 3x ln of 2 come over, and now it becomes minus 3x ln of 2. On the right-hand side, I already have the number 4 ln of 2. He's going to stay put, and now I'm going to red rover, let negative 5 ln of 7 come over, and it becomes positive 5 ln of 7. Now, as ugly as it looks on the right-hand side, in fact, is just a number. There's no variables over there. If you type 4 ln of 2 plus 5 ln of 7 into your calculator, you're going to get a number. Now, of course, if you did type it into your calculator, just to kind of remind you, when you hit ln, your calculator opens the parenthesis automatically for the argument. So you'd have to close the parenthesis after the 2 and after the 7. All right, now, on the left-hand side, normally, if it were just 7x minus 3x, I would get 4x. But I can't do that because even though they both have an x in it, they're unlike terms. So what I'm going to do is I'm going to factor out the x. Factor out the x. Factor out the x. And on the right-hand side, I'll just leave it as 4 ln of 2 plus 5 ln of 7. You don't have to put parentheses around it when you're writing it by hand, because we'll just assume that the first term in the argument without parentheses is the argument. All right, now, believe it or not, this ln of 7 minus 3 ln of 2, that also is just a number. How do I undo multiplying by that number? I'm multiplying by x. I want to get rid of that number. I divide by that number. I divide both sides by that highlighted number. It will divide out on the left, and I'm left with 4 ln of 2 plus 5 ln of 7 all over ln of 7 minus 3 ln of 2. Do I have any x's on the right-hand side? No. So guess what? Is this my answer? That's my answer. And I'm proud of it. Even though it's the bottom line, I'm darn proud of it. So I'm going to box it. Now, could I mess around with this and do something else? Can I play with the log on the back end? Yeah. I could bring the 4 up on the 2. What's 2 to the 4th? 16. I probably would not bring the 5 up because 7 to the 5th power is a big number. So I would leave it as 5 ln of 7. And the bottom, I could leave it as ln of 7. But I could bring the 3 up. What's 2 to the 3rd? 8. So when those numbers are still manageably small, I could do that.
Divide out the ln of 7, so we just have ln of 16 plus 7.
Do these divide out? Is that what you're asking? No, because we can only divide out common what? Factors. And those ln of 7s are what? They're terms. So we can't divide them out. Now, I could do in the bottom if I wanted. I could say it's the natural log of 7 divided by 8. But I'm not going to do that. You know why? Because now it gets that complex fraction look to it. So I wouldn't do that. But I could do either one of these. Okay, we got through example 3b. That's pretty good. Any questions?